Okay. Well, hello, everyone. My name is Aryan. I'm a physics graduate student at Caltech. And I'm going to talk to you today. Hello to everyone. I'm going to talk to you today about physics, and in particular, physics at low temperatures. So first, does anyone have a guess of what is physics? If I ask you, have you heard of physics before? Anyone want to raise their hand? And if you've heard of chemistry, you just did some chemistry. What about physics?
And you can unmute yourselves or you can put an answer into the chat, whichever is your preference.
Light. Okay, I got in the chat, someone said physics is light, and that's a great answer. Physics is a lot more than light, but light, if you want to understand how light works, you need to understand physics. We have magnetic field and water. These are great. These are all topics that come up in physics, and it kind of shows how physics is really the study of everything. Physics tries to understand, someone wrote motion, electricity. These are wonderful, wonderful topics. So yeah, physics is the study of all these things. It's the study of the world around us. And in particular, it's the study of the world at different scales. So we're not just interested in how cars and buses and cars and airplanes behave. We're also interested in how things behave that are very different from our everyday experience. I'm getting a lot of wonderful answers in the chat right now. But notice a lot of these things are relevant to our everyday lives, right? Things like force or motion. But it turns out there's a lot of physics that's at scales that we don't experience. And today I'm going to be talking to you about very cold scales. Yeah, someone wrote particle. That's an example of how physics studies very small things. Today we're going to be talking about cold things. So can everyone see, this area over here? I want you to pay attention to the screen where I have a couple items here. I just have some Tupperware. I have this puck, which will become important later. This is kind of the main theme of the show is in here. I have some grapes.
Can I jump in real quick just to, if people don't know, if up on the upper right under view, if you changed it to spotlight, it will show in large screen what Aryan is doing here.
So should I say spotlight for everyone? Should I just spotlight for everyone?
You can make it spotlight too, yeah.
Yeah, there you go. Can everyone see that? Yeah. So I have, this puck, which I'll talk about later, these grapes, I have some tongs. This is a bunch of magnets. Someone wrote magnets when they thought about physics, and that's a great example of physics. Magnets, they stick to each other because they create force fields, and that'll be important later. Okay, now I want to ask everyone here, what do you think, what's the coldest temperature you've ever experienced? Put it in the chat below. Maybe 0 Fahrenheit, maybe, -10 Fahrenheit. We're going to be talking about very cold temperatures today. And more than talking, I'm going to show you what the world is like when you go to really, really cold temperatures. Someone wrote ice. So ice, water freezes. Oh, someone wrote -55 Fahrenheit. That's the coldest answer I see so far. Someone wrote 0 with no units. That's ambiguous. Okay, so all of these answers are around, from -55 all the way up to 32 degrees Fahrenheit. And these are cold temperatures. By all means, it's 50 degrees. When it's 50 degrees out, I feel cold. But I'm going to be talking to you all today about a temperature that's way, way colder than all of these. And I'm going to be able to show you what happens at that temperature with this. So I've got this tank of liquid nitrogen. I'm going to pour it out here. I'm actually going to put on some gloves first. So what's really important is to be safe. And I'm dealing with very cold objects, so I need to be safe and use some gloves. So I'm putting my gloves on now. Everyone's writing freezing, 0 degrees. And these are all temperatures and concepts that are important. Now, I want you to look here in this Tupperware. Ready? Pay close attention to this. And look what happens. I'm pouring out something into here. Can everyone see what looks like steam? Right? So it looks like I just poured out a bunch of steam, but there's actually a liquid inside here. There's a liquid inside this Tupperware, and that liquid is liquid nitrogen. And liquid nitrogen, it turns out, is way colder than any of the temperatures. Yes, the liquid nitrogen does turn to gas very fast. That's exactly what's happening. So liquid nitrogen is really cold. This liquid here, I would never want to touch it with my fingers, is at minus 321 degrees Fahrenheit. Yes, exactly. Someone in the chat wrote minus 196C. This is really cold. This is about as cold as an oven is hot. So you wouldn't put your finger in an oven because that's super hot. You wouldn't put your finger in this because it's super cold. And you can see it's a liquid. I'm going to raise it up here. I don't know if the camera is focusing, but you can see there's a liquid in there. You know, it's not just empty. Someone wrote negative 999 Fahrenheit in the chat. That's actually too cold. There is nothing that can get you that cold, it turns out. I'm going to put this paper underneath just so I can have something to keep my desk from freezing. So, okay, how cold, though, is this thing? Well, let's put some grapes in and find out. I have a grape, a normal grape here. It's kind of squishy, right? When I knock it on the table, it doesn't really make any sound. I'm going to put this grape inside the liquid nitrogen. And you can see immediately it starts bubbling. And you'll see very quickly that what do you think is going to happen to this grape? I told you that this is really cold liquid here. And I just put a grape in it. What's going to happen to the grape? Glass. Someone wrote glass. That's a great answer. It'll make it become super frozen. Yeah, exactly. Okay. Ice cube. Yeah, let's find out. So I put that grape in for under a minute. You put a grape in your freezer for a minute and nothing happens. I put that grape in for under a minute and you can see it's completely frozen. If I drop it, it makes a sound as if it's rock solid. Everyone, you can hear that sound. And so you can see this is super cold, this liquid. Now, ordinary everyday objects, if you put them in liquid nitrogen and they have some water, they'll freeze. But I'm going to show you something special. I'm going to show you this object here. At room temperature, this object, at the bottom, there's a special metal. And this special material at room temperature is very boring. It's like a ceramic, like your coffee mug. And if I put it on this strip of magnets, nothing happens, right? I put it on the magnets. It's very uninteresting. It doesn't stick. Oh, here's something cool. Can everyone see what happened to the grape? It broke apart. The grape broke apart because water expands as it freezes. So the grape froze completely solid, and it froze. And when the water inside the grape turned into ice, it expanded and pushed the grape apart. So it's cracked open. So we've established that this is really cold. In a minute, we can crack a grape. But I'm going to show you what happens now when we put this object in there. And it's going to undergo a change. So this change is something that physicists study. Physicists study how things change when they get really cold. So I'm putting it in there. And you can see it's bubbling. And that's because the puck I put in is really hot compared to the temperature of the nitrogen. What material is the puck? This is a great question. So the puck is an insulator. It's mostly styrofoam. But underneath, there's a ceramic called YbCO. Stands for yttrium barium copper oxide. So it's a man-made material. And this man-made material changes its behavior when its temperature becomes super cold. And as we all know, right, water is a great example of something that changes its behavior when it gets cold. When it's hot, water is a steam. It's a gas. When it's a room temperature, water is a liquid. When it gets really cold, water freezes into ice. So we have a guess here that it won't freeze. And I'm going to tell you that, yes, indeed, this won't freeze, but something else very interesting is going to happen. I think I've got enough nitrogen in there. So I'm going to now take this object and take it out of the liquid nitrogen, the YbCO. YbCO is the name of the material. And you'll find that it behaves completely differently. Just like what happens when you take water and make it cold, right? Water, when you make it cold, changes. Ice is still made of the exact same stuff as water, but you would ice skate on ice. You wouldn't ice skate on water. You would fall right through. So it behaves very differently. And now I'm going to show you this very different behavior today. So remember, these are a bunch of magnets. Someone guesses it's going to be magnetic. Well, let's see. So I've got it here. You can see it's not really frozen. It's still, very much like it looks the same. It's just got all this nitrogen, and it's very cold because it's steaming. I'm going to put it over the magnet. Now, you can't see, so I'll tilt it to show you. But what's happening is that the object is floating. The YbCO puck is floating above the magnet. Does everyone see that? Yeah. I wish, you don't know how much I wish I could show you this in person. Because as cool as this is here, it's even cooler when you're seeing it with your own eyes.
It's
So what is
magnetized.
what's that?
No way. No way. No way.
So
This is so
Magnetized.
yeah, so one guess is it turned into a magnet. Okay, so one idea is maybe this is a magnet. But I want to remind you of something. When two magnets come close together, they stick, right? They don't let go. But here, the puck isn't sticking, it's floating. So this isn't an ordinary magnet. Now you might say, hold on. Sometimes when I've put two magnets together, they push apart. Now, if that were the case, how could we test that? Maybe the puck is getting pushed away. What if we turn it upside down? It still stays there. So this YbCO, this puck that at room temperature wasn't doing anything interesting, I made it cold and it levitates above these magnets. And it'll actually move around the magnets like a little track. Is that like a maglev train? It's repelling. But if it was repelling, I wouldn't be able to turn it upside down. The fact that I can turn it upside down means that this isn't ordinary magnetism. This is something very special. Now I'm going to put it back in here to get cold again. And while we do that, I'm going to pour some more nitrogen out. And I'm going to talk a little bit about what we just saw. Yeah, so this object, when it gets really cold, it changes its behavior and it turns into something we call a superconductor. So if there's one word that I want you to remember from today, it's superconductor. Superconductors are really special because when they're hot, when they're at room temperature, they don't do anything interesting. I'm going to pour some more nitrogen out. But when they get cold, superconductors completely change their behavior. So we're pouring out some more nitrogen to get our superconductor back to be cold. We've submerged it actually and poured a lot of nitrogen out. So superconductors are a very special type of material that only happens at low temperature. So as you saw at high temperature, the YbCO didn't do anything interesting. This is very similar to water, right? If you have ice and you heat it up, it'll melt. And the exact same thing is happening here. When we cool this down, it changes into a superconductor. And when it heats up, it loses the superconductivity. So we'll see that now. I've got it. It's very cold. I'm going to put it on the track. Okay. It's firmly on the track. You can see again that it's levitating, right? No strings attached. Very much just physics. Only physics. I'm telling you now that this is not a magnet because magnets either stick or repel, and this is doing neither. It's staying there. And then I can push it closer. So if I push it closer to the magnet, it'll stay there. It'll stay a little closer. If I pull it further, it'll stay further. I can even twist it. So can everyone see how the arrow is pointing in this direction? See this this diamond is, maybe I put it here. This diamond is pointing that way, right? If I turn it very gently and release, it snaps back. I want to try it again. So I'm going to turn it. So very gently, if I can. It's kind of tricky with these gloves, but I can turn it there. And when I release, it snaps back. So in addition to floating, it has a memory. This object is interacting with the force field the magnets produce. So magnets know about each other because they make an invisible force field. You can't see it, but the magnets, that's why two magnets that are separated can stick. When this YbCO, when the superconductor sees the force field, it grabs onto it and doesn't want to let go. And it never wants to change how much of the force field it's grabbing onto. That's why it doesn't want to get closer. It doesn't want to get further. It's happy where it is. If it's happy where it is, how come it's willing to go left and right? Does anyone have any ideas? Why does it go easily left and right, but it doesn't go, in the other directions at all? It doesn't fall off, but it goes left and right. It doesn't go to the side. See, I'm holding it like this. Why does it go left and right, but not any other directions? Any guesses? Did I get any comments in the chat, maybe?
Because it's tracked into the metal.
So it's being, someone had mentioned because I'm moving it, but I would point out that gravity is also trying to move it, right? It's floating, but there's something special about this direction compared to any other direction. What happens? Imagine you're the puck and you're standing here versus you're standing over here, and you look down and you see some magnets. Do the magnets look different in one part versus the other part? Or do they look the same? They look the same. We say that there's a symmetry here, that as you move up and down the track, the magnets look the same. Someone said it's magnetized very hard. And I want to point out, this is not a magnet. It's a superconductor. Now, you'll also notice what just happened. It fell. If I turn it now, it falls right off. So even though this YbCO is so cold that you can see the nitrogen evaporating off it, even it's so cold that I have to use gloves, it's too hot. It's too hot to superconduct. So superconductivity happens at extremely low temperatures, temperatures that you can't get on Earth unless you use liquid nitrogen. Now, someone mentioned maybe it's because of the Earth. I want to point out this would happen regardless of where we were. This would happen if we were in empty space. This would happen if we were, on Earth. No matter what, this would happen in a vacuum. This would happen without gravity, with gravity. This is just a property of temperature. When this object gets cold, just like how water turns into ice, this YbCO turns into a superconductor. Oh, we have a great question. What are some other superconductors? It turns out there's plenty. There are a few other man-made superconductors that will do sort of this at, say, around liquid nitrogen temperatures. There's a lot of superconductors that at around -400 Fahrenheit, so colder temperatures, they're metals that will turn into a superconductor. Aluminum is an example. So you know about aluminum in your everyday life, and it turns out aluminum will turn into a superconductor, but the temperature has to be much colder than what I can show you today, much colder than -400 Fahrenheit. So superconductors are actually used in MRI machines, it turns out. And the reason for this is, in addition to levitating above a magnet, superconductors allow electricity with no resistance. So I want you to take your hands and rub them against each other. You notice how your hands get hot, right? That's because of friction. Your hands are rubbing up against each other and they're getting hot. Now, when electricity flows through a wire normally, the electricity bumps into the walls, and just like your hands, the wire gets hot. That's why your computer or your phone gets hot when you use it a long time. If you made a wire out of a superconductor and got it cold so that it was superconducting, it would never get hot when you passed electricity through it. So that's something that's very special about superconductors, in addition to what I've shown you today. And that's why it's used in MRI magnets, because you're able to sort of pass electricity through wires without them heating up. They're also used for quantum computers. And I'll talk about that. Someone asked, does it only levitate above magnets or other materials as well? It has to be a magnetic field. So if we can actually test it with at least the wood, right? I have this wood table. If I put the superconductor over the wood table, not much interesting stuff will happen. It won't levitate. And that's because it specifically has to do with magnetic fields. So I put it over my table, nothing. I put it over the magnet, and it levitates. Now, why is this happening? It turns out if you want to understand this, you have to understand something called quantum physics. Now, if you've seen the movie Ant-Man, maybe you've heard of the word quantum before. And it turns out that quantum physics is a set of rules that we can use to understand this sort of behavior. But quantum physics is way more than that. Quantum physics allows us to understand very cold objects. It also allows us to understand really small, tiny objects. A lot of the chemistry that you talked about in the previous demo is actually, we understand it because we understand quantum physics. Quantum physics is very different from the rules that we use to explain ordinary objects like cars and planes. They're really wacky rules. And just to give you a flavor, if you were behaved according to the rules of quantum physics, you could be in multiple places at once. You could be, in your room, at home, at school, all at the same time. Your arms could be in one place and your legs in another. You could walk through walls. It sounds wacky, but those are the rules, quantum physics, that we need to use in order to describe this. There were some last questions in the chat. Is there a way to do this without nitrogen? It turns out that you can do this without nitrogen. You just have to get it cold enough. Nitrogen is a very convenient way to get it cold because the nitrogen is very cheap. We use it all the time in science to make our experiments cold because all kinds of stuff happen at cold temperatures. So nitrogen is the easiest way, but you could use other methods if you had available some liquid helium. Someone asked, what's the hottest superconductor? That is a great question because this is an ongoing site of research. There is no such thing as a superconductor that will superconduct at room temperature at normal ambient pressure. But it turns out there are superconductors that will work when it's really, like when it's at room temperature and the pressure is very high. So scientists are still trying to understand this. If you gave a scientist a random material, they can't tell you if it's a superconductor or not until they do the experiment. But hopefully one day we'll be able to understand superconductors and build them at room temperature. One last question. Someone asked, why won't it work when it's hot? The same reason why ice melts into water. At a certain temperature, the material changes. When it's hot, all of the stuff, the atoms inside here are doing their own thing. They're all moving independently. When it gets cold, they stop moving so much and quantum physics can take over and cause them to move together, move in sync. And it's when they move together, according to the rules of quantum physics, that you get superconductivity. So that's the demo today. I hope you see that the world is really magical. And physics is about studying that magic, especially when it involves scales of reality that are very different from what we're used to. Today, we talked about low temperature. Oh, someone said, will all superconductors levitate over magnets? Not all will levitate. Some will just fall off and push the magnet off. It's a specific type of superconductor. They call it type 2 superconductors that levitate above magnets. And those are the ones we don't fully understand yet. So this is an area of ongoing research. Maybe one day, one of you can contribute and you might be able to build room temperature superconductivity. Thank you so much for your time. Do they work with electromagnets? Yes, but you need the magnets to be really strong. And it's hard to get electromagnets to be so strong. So I just use these permanent magnets, which are pretty strong.
That's amazing.
I have a question.
I just want to make sure everybody knows that the next speaker starts right now. So we want to make sure that we don't, have them not have their audience. But I don't want to prevent Arian from answering any questions.
Yeah, thank you everyone for coming by. Feel free to go to the next room. And if you stick around, I will stick around as well so you can ask some questions.
And also I can put our email in the chat and you can always email us questions. You can also join our Ask a Caltech Student Facebook page and then ask questions, and students like Arian will come in and answer questions that kids have.
I have a question.
Yeah, go ahead.
I don't really have a question. It's just that I wish that I could create things that clothes that people can use to go inside walls and get out.
Yeah. So this stuff I told you about the rules of quantum physics, it is really wacky. But it turns out it's really, really hard to do it at our scales, or else we would have seen it, right? We don't see things going through walls. And that's because when your walls are like multiple centimeters thick, it's impossible to see these effects I'm talking about. But when things are really tiny, then you can see these quantum effects really clearly, or as you saw today, when things are really cold. But it's still an ongoing sort of research to try to see what's the biggest quantum thing you can build at room temperature. So that is currently still an open question.
Thank you.
Yeah, thank you for the question.
All right, I'm going to stop recording.